Okay, this movie will, I'm sorry. Okay, this movie will be for pages 113 through 118 of what I've assigned. Um, 113, 114, 115, 116 are very, very similar. So I'm going to do 113 and then we're going to kind of go a little faster through them. So it says, let f be a function defined on the closed interval -3 to 4 with f of 0 equal to 3. The graph of f prime consists of one line segment and a semicircle as shown above. So this is a graph of f prime. And then they ask questions like, for example, on what intervals is f increasing? Find the x-coordinate of the point of inflection. Find the equation of the tangent line to the graph at the point 0, 3. So before I even do this, I'm going to draw number lines for f prime and f double prime. And if you understand the number lines, these questions are very easy to do. So the number lines, if I'm given a graph of f prime and I'm trying to fill out the f prime number line, I am looking to see whether the graph is above or below the x-axis. So from -3 to -2, the graph is above the x-axis. So we are looking at a positive first derivative. Then we skip below the x-axis till we get to 2. And at 2 we have a 0, but we are below. And as we pass 2, we kind of dip back down below. So there's our f prime number line. Now I want to graph the f double prime number line, which, since this is the derivative of f prime, we're going to look at the slopes. So as we run across here, I'll even kind of go like this, as I do sometimes. Running across, our slope is negative, 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 negative until we get to 0. So the slope is negative till we get to 0. The slope does not exist at 0, so I'm going to put a little u for undefined. But then the slope changes to positive until we get to 2. And then the slope is negative till we get to 4. And here we are. So here is our f prime and f double prime number line. And now the questions are not so bad. It says, A, on what intervals is f increasing? Well, f is going to increase when the first derivative is positive. That happens from -3, because we're closed off there, to -2. The f isn't going to increase. So f increases on the interval -3 to -2. It's not a point, it's an interval. So I'll even say the interval. Because, well, why? Well, the reason is simple. F prime is positive on that interval. Done. So once the number line is drawn, once you do that analysis, the questions are easy. Part B says, find the x-coordinate of each point of inflection. Okay? A point of inflection is going to correspond to f double prime changing signs. So when does that happen? Well, that happens at x equals 0 and x equals 2. Okay? So f has points of inflection at x equals 0 and x equals 2 because f double prime changes sign at those points. You could have also said that f prime changes direction if you wanted to. If f prime is changing direction, that corresponds to f double prime changing its sign. That's another acceptable answer. Part C asks, find the equation of the line tangent to the graph of f at the point 0, 3. So we have our equation of the tangent line. Looks like this. The point 0, 3, we can type in y minus 3 equals the slope times x minus 0. And now we need to find the slope. But we were given a graph of f prime. So this graph is the y values are the slopes of f. So at 0, when x is 0, the y value, the slope, would be -2. So I can put that here. And then technically, you're done. I can leave this like this. I do not need to simplify this on the part 2. Although it would be nice. I mean, it's not particularly hard to simplify this. You could have had this answer. You could have this. Any of these answers would work. And that's it. And so, I mean, that part, this is, I only gave you 3 out of 4 parts because part D we haven't learned yet from this question. But parts A through C are very, very simple. All right. Number 114 is a similar type question. And that's what's nice about this book. It's kind of organized in this fashion that you have these similar type questions. It says, let f be a function defined in the closed interval -5 to 5 with f of 1 equals 3. The graph of f prime consisting of 2 semicircles and 2 line segments is shown above. Okay, so I am going to draw the number lines again. They gave me f prime. If I'm drawing an f prime number line, I'm looking if we are above or below the x-axis. So here we are above until we get to -3. So from -5 to -3, first derivative is positive. Then we're below till we get to 1. And then we are above till 4. We're above till 4. You can see that. And then below till 5. There's our number line. And I'll close it off at 5 because that's all we know about. And then f double prime, again, we're looking for the slopes. So f double prime, slope at -5 is very positive till we get to -4. Then the slope is negative until we get to -1. In fact, we have to be very careful. At -3, since we're at 2 semicircles, if you kind of think about a circle for a moment, at this outer point here, this is a vertical tangent. So let's just be very careful about it. At -3, technically, the second derivative is undefined. Okay? But it's negative everywhere else on that interval. Then we're positive until we get to 1. And as you notice, at 1 we have a corner, so the slope is undefined at 1. I'll put a u at 1. And then we're positive until we get to 2. At 2 we're undefined because we have a corner. And then we're negative from then on till 5. So there's our number line set up. All right, so part A says find where we have a relative max. A relative max, we're going to look to the first derivative number line. So if f prime is positive, then f is increasing, then decreasing, then increasing, then decreasing. And so we have a relative max at x equals -3 and x equals 4. So at x equals -3 and 4, f has a relative max. Because, well, what's happening? F prime, we need to change its sign from positive to negative. That's how we know we actually have a relative max. So again, once you do the number lines, the questions are not hard. Part B says, from x equals -5 to find final values of x for which the graph has a point of inflection. A point of inflection, we're going to look to f double prime, and we're going to look to a sign change. Well, the sign changes at -4. It doesn't change at -3. It changes at -1 rather, and it changes at 2. So we get 3 inflection points. So f has points of inflection at x equals -4, -1, and 2, because f double prime changes sign at these points. And then part C says, find all intervals on which the graph is concave up and also has positive slope. Well, concave up would mean f double prime is positive. And positive slope, If I want the slope of f, I'm looking to the derivative being positive. So I want to take what's happening here, and I want to look to where my number lines are both positive in a certain area. So let's take a look. Okay, this dragging is not working so well, so I'm going to stop doing it. All right, if we take a look, from -5 to -4, on that interval, both f prime and f double prime are positive. Then, on 1 to 2 here, both f prime and f double prime are positive. So part C, I would say, on the intervals, -5, -4, you could say union 1 to 2. F is concave up and has positive slope because both f double prime and f prime are positive on those intervals. Another way to say this is that you could also say that f prime, it's another way to explain it, f prime is positive and increasing on those intervals. So it's alternate explanation. So for example, you could see so from -5 to -4, the this function, the derivative is positive and increasing. And from 1 to 2, the function is also positive and increasing. All right. Page 115, here's our function g. It's defined and differentiable. Actually, did I finish that last one? Okay, we just had to do parts A through C. Okay. Let's go page 115. The function g is defined and differentiable in the closed interval -7 to 5 and satisfies g of 0 is equals 5. And we have the graph of the derivative. And I asked you to skip part A and do parts B and C. Find the x-coordinate of the points of inflection and work with part C. Part C is a little trickier. But part B, find the x-coordinate of each point of inflection. So point of inflection, I will very simply work with the g double prime number line. But you know what? I want to do g prime anyway. Makes good practice. So again, if we are given g prime and we're looking to form the g prime number line, we're looking for the graph is above or below the x-axis. So we're below till we get to -2. Above until we get to this point, which is 4.5. And then below. And actually at 2, if you were to be particular, at 2 you have a 0, but no sign change. So now g double prime, we're looking at the slope of g prime. So the slope of g prime is positive, so you get to -2. Then we get a corner or a cusp here. So at -2, our slope is undefined, but positive till we get to 0. Then negative as we pass 0 to 2. Undefined at 2 because we have a corner. Then positive till we get to 3. Tiny little interval. And then negative till 5. So where do we get our points of inflection on the open interval? Well, part B, we're looking for sign changes of f double prime. That happens at 0. That happens at 2. And that happens at 3. So at x equals 0, 2, and 3, f has a point of inflection because f double prime changes sign. Another alternate explanation, when f double prime changes sign, it's really saying f prime changes direction. You don't have to have that. As long as you draw your number lines out, you can just say f double prime changes its sign. Part C is a little trickier. It says the function h is defined to be h of x equals g of x minus 1/2 x squared. It says find the x coordinate of each critical point of h between -7 and 5, and classify each critical point as the location of a relative min, relative max, or neither a min nor a max. Explain your reasoning. H of x is g of x minus 1/2 x squared. So in order to find the critical values, I need to find out where the derivative, so critical values, are places where the derivative equals 0 or does not exist. So they gave us a formula for the original function. So we need to come up with a formula for the derivative, which isn't so horrible. H prime of x, since these are terms, we could take the derivative separately. So the derivative of g is just g prime of x. The derivative of 1/2 x squared is just x. Well, we have a graph of g of x. So we want to find out where h prime is equal to 0. So I want to set 0 equals g prime of x minus x. Adding x over to both sides here, we get g prime of x would have to equal x. Now, what does that mean? Well, this is a hard question, and again, this is where the AP gets tricky because this is a question that's never really shown up on the AP before, and this one was, I believe, 2 years ago, and it was hard, and a lot of kids couldn't do this in the whole country. And again, this is where the AP is making us think. G prime of x we have a graph of. Well, what would a graph of x look like if we imposed it on this graph? Well, y equals x is the diagonal going through the origin and going through the point, say, 1, 1. So here is the graph of g of x. I'm sorry, of y equals x. There's the graph of y equals x. And if you notice, it intersects the graph of g prime at 2 spots. It intersects at x equals 3, so that's one solution. And then it intersects here on the circle. What's tricky about this is where does it intersect on the circle? That's the hard part of this question. So where does it intersect on the circle? Well, the circle's equation, if you notice, the circle is centered at 0, 0, and has a radius of 2. So the circle's equation is x squared plus y squared equals 4. Okay? That's the equation of the circle. Okay? But we know we want to get the point where y equals x. So I'm going to plug in wherever I see a y, I'm going to put an x because we want to get the intersection of the circle with the line. So that would happen x squared plus x squared equals 4. And solving this equation, 2x squared is 4. Divide by 2x squared is 2. And x would normally be plus or minus 2, but plus or minus square root of 2. But clearly we want the positive solution because we're in positive x land on the graph. So x is square root of 2. So this is one critical point. This is another critical point. Now, the other places we have to decide are where the derivative, or h prime of x, does not exist. Well, notice h prime of x is written in terms of g prime of x and x. But g prime of x exists everywhere. I want to be very careful here. I'm given g prime here, so I'm not looking for where there's no slope or where there's a corner or cusp, because it's not the slopes that I care about. It's the y values. The y values exist everywhere. The y values would exist everywhere for just x. So h prime of x actually exists everywhere. We're not looking at the corners or cusps. If I asked you where h double prime doesn't exist, then I would look at the corners and cusps of h prime. So we get these two critical values. And now we have to figure out what's going on there. So I'm going to draw a number line for h prime, and I'm going to put radical 2 on it, and 3. And remember, we have a formula for the derivative. It's h prime of x equals g prime of x minus x. So those are the only places where the derivative could change its sign. So h prime of x, I'm going to put in to test, say, on this interval here. Say on the interval to the left of radical 2, I will put 0 into the derivative. Well, that would be g prime at 0 minus 0. Well, g prime of 0 was, I can look at the graph, g prime of 0 was 2. And 2 minus 0 is 2. So along this whole interval, I know the derivative is positive. Then between radical 2 and 3 is the number 2. So I'll look at h prime of 2 being g prime at 2 minus 2. G prime at 2 is a nice easy value to get. G prime of 2 is the y value of the graph we were given, which is 0. 0 minus 2 is negative 2. So on this interval, we're negative. And then if I want to find it on the interval past 3, I'll plug in 4 into the derivative. So that would be g prime at 4 minus 4. G prime at 4, we'll go back up to the graph and look at the y value. G prime at 4 looks like to be 1, but we know it's positive. It's certainly not bigger than 4, so 1 minus 4 is negative 3. So actually, we're negative here. So it says classify each critical point as a location of a relative min, relative max, or neither a min nor a max. So if you take a look, if h prime is positive, that means h, the unknown function, is increasing. And then we're decreasing and decreasing it again. So we want the x values? Yes, we want the x coordinate of the critical points. So now we're going to analyze. X, what it is, and y. So x at radical 2, we have a local or relative maximum. Y, well, h prime changes from positive to negative at that point. And then 3 is neither a min or a max because h prime does not change sign there. And that's that. Now that part's hard. There's no doubt about it. That last question is hard. And I'll be the first to admit, the first time I saw this question, it made me think. Okay? But that's where the AP is coming from. There are, professional people, professors, teachers of 30 and 40 years who come up with these problems, and they're clearly designed to make everybody think, including the teachers. All right. So page 116, here we go again. We have a graph of f prime, and they give us some information. It's twice differentiable. What that means is that f prime and f double prime exist everywhere. Okay. So it says find, again, part A, find the inflection points. Part B, absolute minimum, absolute max. All right, so let's take a look. So f prime, again, we're looking for where, since we're matched up, we're given a graph of f prime, we're looking where this function is below and above the x-axis. It's below, well, technically at 1, we get a 0. But we're below the x-axis before 1, and we are, let me just match this up better with the, sorry. I want to match this up better with the actual graph. So at 1, the derivative is technically 0, but we are negative. The graph is below the x-axis before there and after there until 4. And then past 4, the derivative is positive until we get to 5. Okay, and we'll just do a graph of f double prime here. F double prime, we're looking at the slopes. So f double prime, the slope is positive till we get to 1, because this function's increasing. Then it's negative till we get to 3. And then positive from 3 to 5. There's our number line. And now we can answer the question. So it says find the coordinate of each point of inflection of f. Give a reason for your answer. We're looking at f double prime. And part A looks like we have at x equals 1 and 3. F has a point of inflection. Because f double prime changes sign. An alternative explanation would be f prime changes direction. If you were just looking at the graph of it, either way is fine. Part B says, at what value does f attain its absolute minimum value on the closed interval? So let's think for a moment. If we're taking a look here, we know from -1 to 4, this function's headed down, and then from 4 to 5, this function's headed up. So at 4, that's the only bottom place we have. So f of 4, or rather at x equals 4, we have an absolute minimum. At x equals 4, there is an absolute minimum since f prime changes from negative to positive only at x equals 4. Then it says, at what value of x does f attain its absolute maximum on the closed interval -1 to 5? This part right here, this part we have not done yet. So you are not responsible for this. But what you would be responsible for understanding, that's not how to spell responsible. Let's try again. What you would be responsible for understanding is that, hey, on a closed interval, I would want to check these endpoints somehow and figure out what the function value is. This, as you might imagine, is related to the area between the function and the x-axis, but we'll get to that. So you're not responsible for that at this moment in time. So that's something that you're not responsible for. Don't worry about it. Part C says, let g be the function defined by g of x equals x times f of x. Find the equation for the line tangent to the graph at g is at x equals 2. Well, our tangent line equation is this. At x equals 2, we can fill that in. We need the y value and we need the slope. Well, we know that g of x is x times f of x. So g of 2, which would be our y1 value, equals 2 times f of 2. Well, f of 2, they told us, they were very nice and told us f of 2 was 6. So sometimes you have to go back to that beginning part of the problem and get some information. So 2 times 6 is 12. That's your y value. Now, to get the slope, we need to take the derivative. Well, g of x is x times f of x. So to take the derivative, we're going to use the product rule. So I'll break this up, and we'll take the product. And so g prime of x is x f prime of x plus f of x. And so now g prime of x, so rather we want g prime at 2, which is 2 f prime at 2 plus f of 2. 2 times something plus what they told us f of 2 is 6. F prime at 2, I can go to the graph and grab it, because I know this is a graph of f prime. F prime at 2 is the y value of this graph, which would be -1. So 2 times -1 is -2 plus 6 is +4. This would be your slope. And this would be your tangent line. And I would, on a part 2, that would be it. I would not do anything with that equation whatsoever. I'd be done right there. All right, one more for this video. This one's a little different. It says, let f be twice differentiable function such that f of 2 is 5 and f of 5 is 2. And it says, let g be the function defined by g of x as f of x. And then it says something like this. It says, explain why there must be a value c from 2 to 5, such that f prime of c is -1. Well, if we do a little baby sketch here of, they told us f of 2 was 5. Then they told us f of 5 was 1. F of 5 is 2. And we know the function's twice differentiable, so that means f prime, f double prime exist. So on a graph, what that means is f is nice and smooth. No corners, no cusps, no nothing. So maybe here's an example of f. And what they're saying is explain why there must be a value of c between -2 and 5, such that f prime of c is -1. And if you notice, if you connected this, if you made the secant line out of this and took its slope real quick, the slope would be 2 minus 5 divided by 5 minus 2, which is -3/3, which is -1. So since we're twice differentiable, the mean value theorem guarantees at least one value of c, so that c is between 2 and 5, such that f prime at c is equal to -1. And we showed, this is really important, you should show a calculation of where that number -1 is coming from. And you do want to cite the theorem, or at least explain that somewhere along the curve, since the function is differentiable, and in this case, in my curve, it's actually two places where the slope would be -1, it would match up with the tangent line. I'm sorry, the secant line. Then it says, part B says, show that g prime of 2 is equal to g prime of 5. And then it says, use this result to explain why there must be a value of k between 2 and 5, such that g double prime of k is equal to 0. Interesting. We have not done something like this, but it show that g prime of 2 is g prime of 5. Well, they did tell us that g of x was f of x. So we can find a formula for g prime of x, which you would get points for. It's g of x is f of x, so it's f of stuff. We're going to use the chain rule. So the outer function is this first f. So the derivative of f is f prime of the stuff times the derivative of the stuff, which the stuff is f of x, so the derivative is f prime of x. So now we will use this formula to come up with the value of g prime of 2, to come up with a value of g prime at 5. G prime of 2 would be f prime of f of 2 times f prime at 2. Well, they were nice enough to tell us before that f of 2 was 5. So f of 2 is 5. So we're really multiplying f prime at 5 times f prime at 2. We don't know what those values are because all we know is f of 2 is 5, f of 5 is 2. So I'm going to leave this like this for a moment, because all they did was they asked us to show that g prime of 2 and g prime of 5 were the same. So we're going to go back to g prime of x here and plug in 5 and see what happens. Well, we get f prime of f of 5 times f prime at 5. And it so happened that f of 5 was equal to 2. And if you notice, these two things are identical. So we showed why g prime of 2 is equal to g prime of 5, as long as you make this connection that these two are equal. All right, then it says, use this result to explain why there must be a value k between 2 and 5 such that g double prime of k is equal to 0. Well, if you think about it, what we know now, if I were to try to draw a g prime graph, okay, we would know that at 2 and 5, I have two of the same y value. I don't know what the y value is, but I know that they're the same. So if we think about this, and we know this graph is nice and smooth, they told us that before. What this would imply is that, hey, g double prime, the slope of g prime, would have to be equal to 0 by Rolle's theorem. So by Rolle's theorem, and by the way, just as a technical point, since g of x is f of x and f is differentiable, the composition, if you compose two differentiable functions, you get a differentiable function. So there's no corners when you compose two things that are smooth. So by Rolle's theorem, since g is differentiable and has two equal points, equal y values, at x equals 2 and 5. There must be a place, a value, or a k value, such that k is between 2 and 5, such that g double prime of k is equal to 0. All right, we're going on here. So part C says, show that if f double prime of x is equal to 0 for all x, then the graph of g does not have a point of inflection. So part C is asking us, if f double prime of x were to be equal to 0 for all x, then the graph of g does not have a point of inflection. So, part C. Whoops. We knew g of x was f of x. We now know g prime of x was f prime of f of x times f prime of x. If we're going to ask about the graph of g having inflection points, okay, we have to know about g double prime. So g double prime of x is going to be something. But now we have a product rule that we have to take care of. So over here, we're going to do f prime of f of x, and then f of x. Sorry, f prime of x. So f prime of something, the derivative of f prime of something is f double prime of the something times the derivative of the something, which is f prime. And the derivative of f prime is f double prime. So now we get g double prime of x is equal to, we got to cross this. This is annoying, but it's okay. F prime of f of x, sorry, f prime of f of x times f double prime of x plus f double prime of f of x times f prime of x times f prime of x. Now they told us that f double prime of x is always 0. So that could mean f double prime of any number is equal to 0. So every time we see an f double prime, it doesn't even have to be an x. It can be of anything. It's going to be 0. So this is 0. And this whole thing, f double prime of anything, is 0. So what happens is g double prime of x comes out to be 0 plus 0, or 0. G double prime of x is equal to 0 for any value of x. Therefore, it has no sign changes. If you were to graph a number line of this silly thing, g double prime, it would be zeros all over the place. So, since g double prime never changes sign, because it's always 0, g has no points of inflection. One more and then we're done with this video. Part D says let h of x equal f of x minus x. And it says explain why there must be a value r between 2 and 5 such that h of r is equal to 0. Notice, no derivative here. No derivative is a clue for the intermediate value theorem. So let's take a look. H of x is f of x minus x. Part D, h of x is f of x minus x. And now they told us two values. They said that at the beginning f of 2 was 5 and f of 5 was 2. Let me use that to our advantage here. If we want to evaluate h of 2 would be f of 2 minus 2. Well, f of 2 is 5, and 5 minus 2 is 3. So h of 2 is 3. Then we know that h of 5 would be f of 5 minus 5. Well, f of 5 was 2. 2 minus 5 is negative 3. So if we were to graph points on the graph of h here for a moment, I would have h of 2 being 3, and then h of 5 being negative 3. And so somewhere in the middle here, as long as we knew the function was continuous, we would have to have h of r, I think they called it, h of r being 0. All right, now here's the tricky part. We have to kind of explain why we know h is continuous. All right, h is continuous because f of x is differentiable and x is differentiable. Both pieces of h are differentiable. So f of x minus x is differentiable. I'm just going to abbreviate here. And therefore, if a function is differentiable, it's continuous. And then, since h of 2 equals 3 and h of 5 is negative 3, since 0, I'll even write since 0 is between negative 3 and 3, by the intermediate value theorem, there exists r such that h of r is equal to 0. Commentary on this problem. This is a difficult problem. Very, very challenging. This would be challenging for any child taking the test. I would steer away from something like this on a full part 2. I could ask something, one part of this, to challenge you, but I would not expect this on a midterm that's not the AP exam and that's not being curved the same way. This is definitely a challenging question. And this is the end of this movie.